look at the final exam from fall 2016. So let's write that down. Final exam, fall 2016. And this is going to be question 6. This is a work-related problem. Is that coming through? Okay, good. All right, so we have an inverted conical tank. These are all like strange shaped tanks because they want to see if you understand about geometry. So an inverted conical tank is going to look like this. Okay. They say with the vertex down and the base at the top, and they give us a height. So the height of this thing here, this whole tank itself is height of 18 meters. And then they say it has a base. This is our base right here. It has a base of 8 meters, which means that our radius is equal to 4 meters. Okay, so sort of there's a little trick kind of buried in there in the question itself. Is that focused? Make sure that's focused. Oh, just went out of focus. Why did I do that? Good. Okay. All right. So now, and it says that this thing contains a liquid with a density. Our density is 850 kilograms per cubic meter. Now we have to watch this because this is in a mass unit. So when we're talking about work, we're talking about force times distance, which means, and we're lifting this liquid up to the top. So ultimately, when we go to integrate this, we'll have to multiply by gravity. Gravity. Okay, and then because we're in metric, our gravity is going to be 9.8 meters per second squared. Okay, so keep that in mind. If it's in like foot pounds, actually pounds is it's like maybe slugs per cubic foot, then that would be 32 feet per second squared. But we're in metric, so we're talking about 9.8. So make sure you're looking out for your units because you don't want to be tricked as you go. So we're told that the height of the liquid is 10 meters, so we're filling it up just to 10 meters in height. This is going to give us basically our bounds for integration 0 to 10. We're going to set up but do not evaluate integral for this work involved in pumping and all that. Okay, so now what happens is when we do these problems, we've got a case of essentially similar triangles, right? We're trying to figure out, because our radius is going to be changing as we go. So like the radius at the top here is 4 meters, but the radius just like, you know, a meter down is going to be different than the radius here. It's going to be different than the radius here, then different than the radius here. So we have to be able to come up with a formula for relating the radius to its height. So we're going to set up a ratio for our relationship between the radius and the height, right? Because as we go, right, our radius is going to be changing. So I'm going to think about this as when my radius at the very top, my radius is equal to 4 meters at the top, and then my height at the top is equal to 18 meters. And I can do this by similar triangles, right? So I've got a triangle like this. This is my 4. This is my, sorry, that's 18. And then if I look at, I've got another triangle here, right? This is my radius, and then this is my height itself right there, okay? So I'm just going to solve this for r. When I solve this for r, I'm going to get r equals 4h over 18, which I can divide both parts by 2. So I'm going to get 2h over 9. Okay, some looks like the answer they use z because we're using our z as our height. So if you think about our 3-dimensional structure, I've got my x, y, and my z axis. So I'm going to call z equals my height just to be consistent with the answers in the solution set there. It doesn't really matter. Just make sure that when you do the integral, you do it in terms of h, it's going to be dh. If you do it in terms of y, it's going to be dy. It doesn't really matter. This could be x, and this is y also. We can think about it that way. All right. So now we have a relationship, our radius. So I need to think about the area of the base, right? It's circular, right? They told us before it was a circular cone. So a circle, the area of a circle is going to be pi r squared. So this r right here, this is the r that we need to plug in here. So because our r is going to be changing as we go. We've got a tiny little sliver here, tiny little sliver here, tiny little sliver here. Then I'm going to be adding up and be integrating as I go. So our area, basically for all these little pieces, I've got pi times 2h over 9 squared, because this is our radius squared. Because so keep that in mind. So now when we talk about work, right? I'm going to be talking about, I'm going to integrate over the volume of water that I have. So my water is filled from 0 to 10, okay? And I basically have the density, right? And this is going to be force times distance, okay? So what I need to do is I also need to think about what's the distance that I need to travel as we go. So before we start plugging, this is our force, right? This whole thing is going to become our force times, our force is going to be equal to the density, right? But we need to multiply that by gravity to take that into account. So it's like basically that tiny little sliver of liquid that we have times its density times gravity, because it was given to us in mass units. And then we have to think about the distance that we're traveling. So when I look at my overall, my height is 18, but the water that's here is only going, right, like 18 minus 10 meters. But the water here at the bottom is going the full distance. So I need to have some kind of relationship that's going to talk about the distance, the variable distance that my water is going to go, depending on where that little sliver of water is as it's being pumped up. So I'm going to think about, I'm going to go my total height minus, we're doing things in terms of h, my total height minus wherever I happen to be, right, when I calculate that little sliver. Okay, so this is going to be from 0 to 10, right? Our density, which is 850, times our gravity, okay, times pi, r squared, 2h over 9 squared. And then now times the distance that we need to go. And I'm going to go dh. They called it dz, it doesn't really matter. Okay. Oh, it looks like in the solutions that they have G, it looks like they're putting in G, or they didn't actually plug in a number. So I look at the solution set, they have a G in there, and the G stands for gravity. I don't think that they mentioned that the G stands for gravity. So, and then this is it. We don't actually have to calculate it because it's pretty simple integral when we go to actually calculate it. We just want to be able to set up the integral for it, okay, which is fall 2016.